कब करी? हाँ, कितनी देर पहले करी हुई थी? नहीं तो मेरी आवाज तो नहीं आ रही थी अभी पहले? हाँ तो नहीं, तो मैं बात कर रहा था एकदम, ये चालू हो गई मीटिंग।
हाँ केटी साहब, आई हैव ज्वाइंड. तुम्हारा ऑडिबल, एक सेकेंड.
Yes, sir, you are audible. I heartily welcome you, sir, in 2 weeks FDP program.
Thank you.
Thank you very much, sir. Ritu, kindly give the brief introduction of sir. Ritu?
Yes, sir.
Yes.
So, good day, sir. A very hearty welcome to all the faculty, respected faculty members present with us, and to our esteemed speaker for today. Uh, I would like to tell about the eminent speaker. Dr. B.K. Panigrahi sir is presently working as a professor in the electrical tribology card IIT Delhi, India. Prior to joining IIT Delhi in 2005, he has also served as faculty in electrical engineering department UCE, Urla, Sambalpur, Odisha, India from 1992 to 2005. And techniques to power system planning, operation control, protection and management. Professor Panigrahi is presently also looking into the issues of EV charging infrastructures and the impact of fast charging infrastructure on the grid. He is serving as the editorial board member, associate editor, special issue elsewhere, Ranger, etc. He is also associated with various international corporations in various capacities. Dr. Panigrahi has published more than 500 research papers in various international and national journals. He is a fellow of INAE, fellow of NASI, and senior member of Sir. Today is going to give a talk on swarm intelligence.
Okay. Yeah, thank you. Perhaps I'm audible to each one.
Yes.
Okay. So very good evening to all of you. So
presentation is also visible.
Okay. So I hope my the slide is visible. And just tell me, I'm changing the slide. Is it changing?
Yes, sir. It is changing, sir.
Fine. So I'll talk about today the swarm intelligence with engineering applications, because I know this faculty development program, maybe the faculty from various disciplines are there. So swarm intelligence is a particular area where we need the collective decision making of some agents. Everyone is having its own intelligence, but whenever the intelligence are shared among each one to solve a particular problem, we call it swarm intelligence, because swarm is basically a collective noun, which we read in class 3-4 in English. Okay, so that is the main idea of swarm intelligence. So I will talk about the swarm intelligence with its engineering application. Now, why this swarm intelligence or evolutionary computing or bio-inspired computing, all these, whatever the computing techniques, are basically used for the optimization. Now, when I talk about the optimization, so I want to optimize a certain mathematical function. That means I have to find out what is the minimum value of the function or maximum value of the function if the function x is a vector. So I have to find out x star for what values of the particular variable x1 to xn. If it is a n number of variables are there, the function is maxima or minima. So in mathematics, we call maximization, minimization, etc. But generally in computer science, we call it a search method. So I am searching for a solution in the search space. The search space is n dimensional, where all these n are the number of variables x1 to xn. So in that search space, I am finding out what is the optimal solution, whether it is a minima or maxima. So ultimately, I have to search in that search space for the global solution if there are multiple maxima or multiple minima, because either the function is a convex having a single minima, single maxima, or it is non-convex, multiple maxima, minima are there. So to solve this optimization method, either we have a traditional optimization method or non-traditional optimization method. So I will talk about what is the traditional optimization method. If you look into every optimization algorithm, I need to find a solution. There may be n number of solutions. I'll give you an example. Suppose I have to travel from place X to place Y. Everybody now is looking into the Google map while traveling X to Y. So now the question is, if I want to travel from X to Y, what is my objective function? Is the objective function the minimum distance? If it is a minimum distance, I may get a path. Or if it is not minimum distance, I want the distance may be a bit longer, but I will cover that in a minimum time. So in that particular case, the Google map has to look into the road condition. You might have seen 6 minutes slower, 6 minutes faster, whatever. So it gives you a solution. So to find out the solution in an optimization problem, we have to define what is the objective. Once I know the objective, then that objective can be evaluated either by deterministic algorithm or by a stochastic algorithm. This means that the solution in the search space can be found out either by a deterministic search method or by a stochastic search method. So when I'm talking of deterministic algorithm and stochastic algorithm, then this can be solved by any of the traditional algorithm, like you know that the traditional Newton-Raphson method, the other type of methods are there where I move as per the information of the gradient. Okay, so when I move as per the information of the gradient, then either it is a gradient ascent algorithm or it is a gradient descent algorithm. So I have to stop at a minima or maxima. But if there are multiple minima or maxima, the solution is dependent on the starting point of the solution. That's why in a deterministic search, I may try at the local minima or local maxima because my solution is dependent on from where I'm starting, my initial guess of the solution. Because what exactly you will do, you take an initial guess of the solution x0, evaluate the function f of x0, increment the solution by del x. So a new solution is generated from the old solution x0, that is x0 plus del x. Then evaluate the function again, f of x0 plus del x. So you have y2, that is f of x0 plus del x, y1, that is f of x0, divided by x2 minus x1, that is x0 plus del x minus x0. So this is nothing but the slope. So based on the slope, you go on increasing the step size till the slope becomes 0. So either at the maxima the slope is 0 or at the minima the slope is 0. So remember, such algorithm is a deterministic algorithm. Why? Because your search proceeds in a unit direction. The number of agents involved in the search is one single agent. The search is guided by a fixed rule, that is the information of the gradient or information of the slope. So that's why the deterministic search may lead to a solution, but that solution may or may not be the global maxima. So where this global maxima, whenever there are multiple maxima or multiple minima, the global term comes. So that function is known as multimodal function. So if it is a multimodal function like this, you can see, if you start the initial search from here, you will say this is the maximum. If you will start from here, you will say this is the maximum. If you will start from here, you will say this is maximum. So there are three maxima, and out of the three maxima, this is your maxima, that is global. But you can reach at the global maxima if your initial guess, you start from here. In this zone, your initial guess lies. If the initial guess lies beyond this zone, either on the right hand side or on the left hand side, you may trap at the local maximum. So that's why in a multimodal problem, my traditional search algorithm may fail. Why I'm telling may? Because it depends on the initial. This is nothing but the same as hill climbing in computer science. While you climb the hill, you take a position, you are blindfolded, your eye, take a position, that is x0. Okay, then evaluate by the stick which you have on your hand. Am I at the peak? If the answer is no, then put a step. So you go on. So again, the step size determines whether you will get at the peak or not. For example, if you are taking the initial x0 here and the del x is like this, then you come here. So suddenly with the positive slope, you are coming to the negative slope. So you will oscillate about the maxima because your step size is more. So if the slope is very fast, that means it's a highly slope, then in that case, you need a very small step size. But I don't know the nature of the surface. That's why whether you can reach at the peak or not, it depends on the determination, that is del x. What is the del x size? What is the step size you are taking? So these are the some problem associated with the traditional method. The other point is sometimes the function may be discontinuous. So here you have seen the function is continuous in nature. But if the function is discontinuous, you know, it's very difficult to find out the derivative in those zones. So for such type of problem, I need a stochastic search algorithm. I need the evolutionary computing algorithm. I need the bio-inspired computing. I need the swarm intelligence based algorithm, which is nothing but a multi-agent search. So the number of agents involved in the traditional search method, one, here there are multiple agents. So what these multiple agents do? So in the traditional search, I assume an initial guess of the solution. So here, instead of assuming one initial guess of the solution, I am generating n number of initial guess of the solution. That n number of initial guess of the solution in the search space is known as population in genetic algorithm, is known as swarm in particle swarm optimization, is known as bacteria colony in bacteria foraging optimization, or is known as the number of bees in artificial bee colony optimization. And each individual solution, each individual X0 among those is a chromosome in GA, is a particle in particle swarm optimization, is a bee in honeybee optimization, is an ant in ant colony optimization, is a bacteria in bacteria foraging optimization, is a vector in differential evolution algorithm. So my point is, whatever may be the algorithm, whether it is a swarm intelligence based algorithm or it is a evolutionary based algorithm, so the initial stage is same for every algorithm. Generate n number of probable solution in the search space. You know the dimension of the search space. So that's why my search space must be defined, well defined. In mathematics, if I have n number of variable x1 to xn, x1 is having a lower limit, upper limit. X2 is having a lower limit, upper limit. For example, if I am searching a coin on the floor, so I have two dimensions, x1 and x2. So if it is a room, the length is 0 to 5 meter, the breadth is, let us, 0 to 3 meter. If I am searching something on the three-dimensional in this room, it has x, y, z, x1, x2, x3. So every point is having x1, x2, and the height is x3. So every probable solution you generate in the search space. Okay. And these solutions is generated in a random manner because it is a stochastic algorithm. There is no deterministic algorithm. When I'm searching in the search space, I can't measure, okay, x1 is 2, x2 is 2, x3 is 2. Then x1 1, x2 1, x3 1. So no uniformity. They are randomly scattered in the search space. So you generate a random number for each variable within its limit, x lower limit, x upper limit, for a chromosome or for a particle or for a vector or for an ant or for a bee. So I hope the initial stage is well known. Now coming to the next, this already I have mentioned, this is a traditional method. So in the traditional method, what happens? You may trap at the local minima. If you are starting from here, you move on the information of the gradient, you will stop at this local minimum. Okay. So this is a multimodal function. If this is a multimodal function, actually this function is a Ackley function in 2 dimensions. So you can see there are multiple peaks. Okay, there are multiple maxima as well as multiple minima. So please try to understand. You will get the same information just to visualize it. if you are sitting and reading the newspaper, you cross a paper on your hand, put the crossed paper. So this is a crossed paper. If you look from the top, okay, there are many maxima. If you look from the down, there are many minima. And same thing happens with a egg crate. You have a egg crate in your hand, fold it in downward. If you look into the top, multiple maxima. If you fold it in the upward direction, look from the down, there are multiple minima. So this is basically a multimodal function. Okay, so you will get the multimodal function. So in a multimodal function, to find out the global maxima, I have already mentioned to you what is the solution. The solution is multi-agent search. These are the different agents generated randomly, scattered in the whole search space. So these are randomly initialized agents. Same thing. There is single agent X0, there are multiple agents. Now, once you take X0, you are evaluating f of X0. So similarly, here all the agent in the search space, whether the agent is a chromosome, the agent is a particle, the agent is a bee, the agent is an ant, the agent is a vector, the agent is a monkey. If it is a monkey optimization, whatever, forget about that. I'm not going into that. Okay. So in that case, you evaluate each one because you know the function value. Once you evaluate, what you are doing in the traditional search, you are generating a new solution from the old solution by deterministic increment x0 plus del x. But here I don't go for deterministic increment. So now the question is how to generate again n number of another solution, a set of solution, that is n, from the old n solution. So in GA, what you do, you make pair of the solution. So there are 20, let us 20 chromosome. You select the crossover probability. Let the crossover probability is 0.8. So 20 into 0.8 is 16. So 16 chromosome, that means 8 pair of chromosome will take part in crossover to generate the offspring. So you will get another 16 offspring. Okay. From a set of parents, you will get a set of children. Okay. So that means 16 are there and 4 are as usual. So you are generating 20 new solutions by means of the crossover. But in the particle swarm optimization, which is a swarm intelligence, I don't want this. So the question is, every algorithm is generating a new set of solution from the old solution, that is the property of the algorithm. What is the algorithm you are implementing? If it is a genetic algorithm, there is a crossover and you generate a new solution from the parent by means of the crossover. But if it is a PSO, if it is ant colony optimization, if it is a honeybee optimization, so the generation of the new set solution is different rather than crossover and others. How it happens, I will go to tell to you. So ultimately they move and ultimately all the particle, all the agents will converge at the global. So that is the beauty of this particular algorithm, the swarm intelligence algorithm. Okay. So now there are different methods of the swarming. I'm not going to see. These are the swarm intelligence. You might have seen this figure, the fish pooling. Why they spool like this? This main idea is the collective. They collectively move either in the search of the food or they collectively move to avoid the predator because they are the prey. If there is a predator, they avoid that. So that is the collective intelligence. These are the different collective intelligence you might have seen. The migration of the birds, the bee algorithm or birds flocking algorithm. So all these they go in a group. Okay. So these are the concept of the swarm, and the swarm intelligence comes from this, either this termite or white ant or whatever you can see, ant colony. So I'm not going into the detail. These are the basic understanding of the swarm intelligence algorithm. Okay. So they swarm, because this is the beautiful example. You can see how collectively they build this monument. Okay. You destroy it, you will find a new one very quickly. The more you destroy, the more they will build it for you. Coming to main, I'm not going into the detail of this. I'm going to tell you one algorithm. Actually, Marco Dorigo, they have given this ant colony optimization. But I'll today discuss about the particle swarm optimization, which is the algorithm developed in 1996. No, sorry, 95 by Eberhardt and Kennedy. Okay, so this algorithm, particle swarm optimization algorithm, which is published in one of the conference, but then it becomes very, very popular. So let us, I'll discuss with you how this PSO works. So the PSO, I've already mentioned, it is a stochastic optimization algorithm. Okay, and this technique is based on the movement of the swarm. Swarm means the movement of the birds, how they collectively move. Okay, so it has the concept of the problem solving in finding out the global optimal solution. Sometimes it may not reach at the global optima, maybe it will trap at some other local optima. We'll discuss about that. So that that concept is based on the social interaction, and that concept is based on the self-cognition. I'll talk about these two. So these are the inventor, Russell Everhart and James Kennedy. One is an electrical engineer, the other is the social psychologist. Clear? Now I will explain you this PSO from the very one diagram. This diagram. If you understand this diagram, your understanding of the PSO will be very clear. So please try to understand. Here I want to give you three different dimensions to you. Now I have a function to be optimized. Now let us assume I have a function to be optimized, and that function is f of x. Clear? So if I have a function to be optimized, that is f of x. So now that function, let us, it is having two dimensions. This is one dimension and this is the other dimension. So what I'm doing, I'm generating n number of particles in this source space. So suppose one particle is here, another particle is here, another particle is here, all are random. So now what will happen? Now the first particle is generated with x lower limit, x upper limit. For example, this is 0 to 5 is the one dimension, the other dimension let us minus 10 to 10. So what I can do, let this point is 0. So here this may be 2 and minus 7. So this is one particle is 2. I'm generating a random number between 0 to 5, that is 2. Another random number minus to 10 is minus 5. So 2 minus 5 is one particle. Then I'm generating another random number 0 to 5, that is 1 and 3. So this particle is 1 and 3. So likely I have generated n number of initial particles. So in the search space, all the n number of particles. So now particle is I, which is equal to 1 to n. So I is the number of the particle in the total population, in the total swarm, the swarm size is n. Okay. So all these n number of particles are initially generated in the n dimensional search space. When I'm talking of n dimensional search space, try to understand this is the dimension of the problem J, okay, which is equal to 1 to D. D is the dimension of the problem. So that means there is a variable x1. Similarly, the last variable is xd. This is the D dimensional search space. Clear? So now what I'm doing, now in this case, the dimension of the problem is 2. I can visualize up to 3-dimensional search space, but it's very difficult for me to visualize a D-dimensional search space. But remember, if it is a D-dimensional search space, that means this particular particle will have a dimension 1 to D. So x1 to xd. Similarly, this is another x1 to xd. So all these particles are generated. My point is, you can very well generate this by a simple MATLAB program or Python or somehow like that. You write a program, you know the lower limit of each variable, you know the upper limit of each variable. So for each variable, you can generate a random number between the lower limit and upper limit, and you continue for D number of variables. So in the loop, you can find out now n. So I equal to 1 to n, j equal to 1 to d, you generate end. So all particles are generated, and they are generated in iteration number 1. So k is the iteration number. I can write iteration k equal to 1 to total number of iteration, ITER total. So I hope I have introduced here 3 variables, I 1 to n, that is the number of particles in the search space, j 1 to d, each particle is having d dimension, and k is the number of iteration. So I am starting the search, k equal to 1. So for k equal to 1, for I equal to 1 to n, for j equal to 1 to d, I have generated all the particles. I have evaluated all the particles, and every particle is given at the initial stage a push, a velocity. So now whatever particle I am generating in the d-dimensional search space, there is a position in d-dimensional search space, as well as there is a velocity in d-dimensional search space. What do you mean by velocity in d-dimensional subspace? For example, I have a body here in the 3 dimension. So initial position x1 is 2 meter, x2 is let us 1 meter, and x3 okay, x1 2 meter, x2 is 3 meter, and x3 is 1 meter. So this is the position I have generated, but I have given it a push. So when I am giving it a push, now it goes here. So now you see there is a change in velocity in x, change in velocity in y, and change in velocity in z. That means every particle is given an initial position and an initial velocity in every direction. Clear? So every particle initially given a position and given a velocity in each dimension. Clear? Fine. Now I have evaluated. Once I evaluated, now next question is how the particle, because now I can say the particle comes here to here. These are the 2 positions. You can see this is one position, this is the other position. So it moves from this to this. So there is a change in x, there is a change in y, and there is a change in z. There is change in x1, there is change in x2, and there is change in x3. So all these change is because of the velocity in x direction, y direction, and z direction. Clear? So how this new position is generated? Now new position at iteration 2, next position iteration 3, next position iteration 4. So I can tell the particle moves from this position to this position, maybe to this position. I don't know. This will move like this. So every time it has changed its direction. So now the question is, what will be the velocity of the particle I in dimension d at k plus 1th instant? So please try to understand. This is very simple. S is the position of the particle. Which particle? I equal to 1 to capital N. In dimension d, fine, j equal to 1 to d, k is the iteration. This is the position of the particle. How it comes to this position in d dimension? With a velocity vk. So vk is the velocity of the particle at kth instant in dth dimension. Now if it will move in this way, it will go and collide to the wall. So do I want the particle should be moved on the same direction, or the particle should change its velocity? So to change its velocity, I'm giving you a simple example. Very classic example. Let us, I have a class. In that class, it is engineering. Let us, I have to go from semester 1 to semester 8. So k equal to 1 to 8. Assume in each semester, there are 5 subjects. So j equal to 1 to d, that is 1 to 5. 5 subjects they will read in each semester. And the total number of students is 20, j equal to 1 to 20. So now suppose everybody is in 3rd semester. So k equal to 3. So when everybody is in 3rd semester, all the 20 particles, but they may have secured different mark in all those 5 subjects. So they have different position. Now among those 20 in the 3rd semester, somebody may be the best one. So how everybody will think to be the topper at the end of the 8th semester? So that is the point. That is the concept of the swarm intelligence. So how a particle I in a particular iteration k will change its velocity in dimension d. Okay, so when it want to change its velocity in dimension d, will it continue with the same velocity as in the previous? That means the velocity of the particle at k equal to the velocity of the particle at k plus 1, or no, I want that. What was my best velocity till now? Because I'm in 3rd semester, my position is 10th, but I was 3rd in 1st semester. So in k equal to 1, my position was very best because I was evaluated 3rd. So that is my personal best, that is VP best. So VP best is the personal best of the particle, which is not in the present semester, but it was previously. So I look back. When I look back, because you are already at kth iteration, you have already covered 1 to k. Okay, iteration 1, iteration 2, iteration 3 up to iteration k. In iteration k, your velocity is Vk. But somehow between 1 to k, somewhere your velocity was better and your position was better. So that is Vp best. Now, in the present iteration k, among the 20 particles, which particle is the best? That's velocity is Vg best. So I hope it is not difficult for you to find out Vp best and Vg best. Vg best is evaluated in the current iteration k among 20 particles I equal to 1 to n. Vp best is evaluated at the current position, but looking into the previous. So now I have three vectors. One vector is Vk, the other vector is Vp based, the third vector is Vg based. So I will generate a new vector that is Vk plus 1, which is the weighted average of these three. Neither I want to move in this direction, nor I want to move in this direction, nor I want to move in this direction. I want a vector weighted. So this velocity is given a weightage, this velocity will given a weightage, and this will be given a weightage to find out the new velocity. So that with this new velocity into the time is the iteration, one iteration time, I'll go to this position. Okay, so the particle changes its position, and again remember, particle I in d dimension changes its position from sk to sk plus 1. Similarly, you have to change its position for every dimension. That completes one particle movement. Then we'll go to particle 2. Change its position in d dimension. Go to particle 3. Go to particle 4. So every particle looks into previous back, but global is one in the same iteration. So I hope you have understand. So point is, sk is the current position, current searching point of the particle. Sk plus 1, it will be new position, which is dependent on my current velocity, Vk, my velocity based on my personal waist, Vp waist, and the velocity based on the topper, that is Vg waist. So I'll write it mathematically very simply by this form. So each particle tries to modify its position using the information of the current position, which is Vk. Sorry, the current position is Sk. The current velocity, that is Vk. The distance between current position and P base, that means where am I and what was my previous best position. And the distance between my current position, where am I and what is the topper. So in classic, I can tell today my position is 10th in third semester because I am reading 3 hours a day. But in first semester, my position was third, I was reading 7 hours a day. So that difference I want to make lesser. Okay. Similarly, presently my position is 10th, but somebody is topper in the class and he or she is reading 10 hours a day. So I have to make that difference. So that those are the two things. You want to minimize your distance from your own best performance and the performance of the topper or the best particle at this particular stage. So that is the thing. Based on that, you can see this equation. These are very, 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 very simple. You can write this program on your own in any of the language, you know. So the velocity of particle I in dimension d at k plus 1th instant equal to your Vik, the present velocity in dimension d at kth instant multiplied by a factor omega. So omega is known as inertia factor. Okay, this is the inertia. I want to give the acceleration to this. Plus your present position, that is Sik, your own best position out of the previous history, that is P best I. So remember, that's why I am writing here P best I, my own best, personal best. So this difference is multiplied by a C1 is a constant and a random number. So you can tell the whole one is a phi 1. Okay. Similarly, C2 is a constant and random number. So this will be phi 2, which is multiplied with G best. That's why I'm not writing G best I, because among these I equal to 1 to n, 20, 1 is the best. That remains best for that particular iteration. In class, in third semester, only one person is the topper. Either he was the topper in second semester, I don't know, or there is no guarantee he will be the topper in the fourth semester. So that's why every iteration, the topper, the best performer may change. So that's why I want to compete with that. So this is G best minus Sik. So this is a very simple algorithm. So once you get this, then you can write the next step is Si, the position of the particle I at k plus 1th instant will be position of particle I at kth instant plus the new velocity, whatever you calculated for I at k plus 1th instant into the time, which is equal to 1 iteration. So this is, so you can see this equation. So remember here, under here, this is a very good mathematical, because when I am talking of the movement of the particle, this is dynamics, the change in position. So every dynamic system is governed by a mathematical equation. Change in position, dy by dt, change in with respect to time. Here dt is equal to 1. Okay. So when I can describe the movement of the particle, the motion of the particle in the search space because of the change in its position by a mathematical equation. It can be described by dy by dt, the change in position, or dx by dt, the change in position. X is the variable, each variable with respect to time. So when this is basically the same thing, position and velocity, you have two vectors. And this differential equation in discrete domain can be written as a difference equation, because dy by dt is nothing but yk plus 1 minus yk minus 1 divided by del t. Del t is 1. So position sk plus 1 minus sk is the change in position. Vk plus 1 minus vk for each particle is, so this can be represented by a state space equation. Because when you are writing a state space equation in control, because anybody have studied the control, you can study the movement of the particle in the dimension, and this movement control is dependent on, because it is x dot equal to ax plus bu. Okay, so you can frame it as a mathematical equation, x dot equal to ax plus bu, and by that you can see how the particle is moving in the search space by applying your control theory. And how can you make this movement of the particle a streamline motion? They converge to the solution. So you can study the stability of the swarm. You can study the convergence of the swarm by various mathematical analysis. So for that, you can find a beautiful paper by Passino and Gaggi. Okay, if you search the stability of the swarm in Google, you can find a paper by Passino and Gaggi. Okay, this is the stability of the swarm. Actually, Passino is the inventor of this bacteriophorizing algorithm. So why I am telling this? Because anybody from mathematics and other background or control theory background, you may derive all this. You may find out the parameter. Now, what are the parameters which govern the movement of the particle in the search space? Fantastic. This is omega, phi 1 and phi 2. So depending on the value of the parameter omega, phi 1 and phi 2, your movement of the particle is governed in the search space. So what I can tell you very simply, for example, this is my search space. I have a particle here. Let it has to reach the global point here. So it may happen that this moves like this, it comes like this, it comes like this, ऐसे move करके it may come here. But it may have that you may design the algorithm so that it will go to first iteration, second iteration, third iteration, fourth iteration. Now you can see both the movement, both the motion. One is a controlled, another is uncontrolled manner. So while it is uncontrolled manner, this may diverge. You may not give the guarantee for each particle to be converged to the solution. So the convergence of the algorithm, the stability of the algorithm can be studied by this parametric study, how to change omega, phi 1 and phi 2. Okay, so this is the very basic concept of the PSO which is developed initially. So here Vik is the velocity of ith particle at kth iteration. Omega is a weight function. C1 and C2 are also weight function, and random, the uniform random number generated. So you can see now, this is suppose particle 1, x1 at time t. Okay, now it is moving as per its original velocity is black. So if we leave it, it go in the black direction. But what is it doing? This is one vector, the black one. It is showing its previous best position was this one, and the global best is this one. So you take the vector addition of these three, the black, the blue, and the pink, these three vector, so that the new vector is originated. So it moves from this point to this point. Similarly, the second particle, this is its original velocity. It is its p-best velocity. Okay, this is the global velocity. You add, it will move. So this particle will move in this as per the mathematical formula which I have already given to you. So there is a beautiful animation. You can see these are the different particles in the search space, and you know that in this particular search space, one is the global maxima, this one is the global maxima, these are the local maxima. Here is a local maxima, here is a local maxima, here is a local maxima. So what you will do, you generate all the particle randomly, and every particle is given a random velocity. That's their direction. So now after iteration 1, this is the movement. Iteration 2, this is the movement. Iteration 3, this is the movement. Iteration 4, this is the movement. So you can see after fourth iteration, some particles are trapped at local minima, and some are nearer to this global. So now because of your third term, that is G best minus SIK. So somewhere out of this, one will be G best. Let this is G best. So G best minus SIK, this vector, or G best minus SIK, this vector, because of this term, So this interaction with the G-waste is a social interaction. Comparing your own performance with your own present performance with your own best performance in the previous is your self-cognition. So the whole movement of the particle is dependent on two psychological factors. One psychological factor is self-cognition. Yes, I can do it. Another is social interaction by the help of my peer group. So this is an algorithm which is beautifully balanced by the global search and local search. I'll come to that. So because of this social interaction, all the particles which are trapped at the local minima at a particular iteration here will come back and everybody is converged to the global solution. So that is the beauty of this algorithm. Whereas in genetic algorithm, you generate a solution, only one will be the winner. But here everyone will be the winner. That means all the 20 students at the end of the 8th semester, k equal to 8, irrespective of the marks secured by them in different subjects, but the total is same. They are evaluating same value. Okay, so that is the main beauty of this particular algorithm. This small mathematical function, I have shown you how to update it, but I don't want to discuss it. You can find out. I'll share this slide. So I want to optimize fx equal to x into x minus 8. Okay, but never try this optimization by swarm intelligence algorithm. Then the paper which will communicate will be immediately rejected, because this is a very simple convex plot. If you look into plot, this is like only simple one minima. So here, just for demonstration purpose, I have used it so that you can understand it. So if this is a single variable, fx equal to x into x minus 8, I want to optimize this. So what I'll do, you see, here there is the range of x is minus 10 to 10. So for what value of x between minus 10 to 10, fx equal to x into x minus 8 will be maximum or minimum. Okay, so your objective is either to find out the maxima or to find out the minima. So what exactly you are doing? Let us initially, I am taking 4 particles. So for all these 4 particles, every particle is given a random position and random velocity. There is a single variable. So if it is a single variable, generate a number between minus 2, 10 to 10, that is 7, and another velocity minus 10 to 10, that is 3. So the first particle is given an initial position 7 and initial velocity 3. The second particle given an initial position minus 2 and velocity 5. So likewise generate 4 particles. Once you generate, then evaluate. Once you evaluate, this is evaluated as per the position. So if you put 7 into 7 minus 8, that is minus 7. Minus 2 minus 8 is 20. 9 minus 8 is 9. Minus 6 minus 8 is 84. So if it is a minimization problem, so I can see out of these 4, which is the global best? The first one, if it is a minimization. If it is a maximization, then this will be the global best. So it is a minimization problem, I am telling. So this is the global best. So at the first iteration, when you will go for global best, now you see, no one is having the previous best. And global best itself will not be updated. So if I will update that, so now you go on updating for each one. The particle 1, the velocity omega is 0.5. Its position is, velocity is 3. So particle 1 velocity is 3. So you can see omega into velocity, that is 0.5 into 3, plus C1 is 2. A random number between 0 to 1 is 0.6. Then P best, because in the first iteration, P best is itself 7 and no previous. So 7 minus 7 is 0. Okay. And the global also 7. So this is only 1.5. So new velocity is 1.5. So now your new position becomes, because initial position was 7, now 7 plus 1.5 is 8.5. Similarly, the second particle we want to update. Now second particle, the velocity is 5 into omega 0.5. So 0.5 into 5, then 2. Okay, C1 is 2, a random number between 0 to 1. So you go on. This is a simple mathematical formula I don't want. So you can see all these particles, they are updated. And finally, after 4 iterations, you can find all the particles are converged. For x equal to 4, the minimum value is minus 16. Okay, so if we put x equal to 4, uh, 4 into 4 minus 8, so you will get the value is minus 6. Okay, so this is the simple one. Similarly, my point is you can do it for other function. Here I have shown it for a 2-dimensional surface for the Rastrigian function. The Rastrigian function is an. I equal to 1 to n xi square a cos 2 pi x. So this function you have to manage. So this is a two-dimensional subspace you can see. So if it is a two-dimensional subspace, so I have to generate the initial vector. Now if you see the initial vector, because here the value is minus 5.122 to plus 5.12. So you generate a random number minus 5.122 plus, but it has two dimensions. So initial particle you can see, this is the first position of the particle, this is the second position of the particle, this is the third one of the particle. So like way you generate it, you evaluate each one, then you find out what is the individual base. So you can see all these particles now they will be updated. So 1 will be here, 2 is here, 3 is here, 4 is here in the subspace, 5 is here. Now in the next iteration, their position has been changed. See, you can see this one. Sorry, this one. Next iteration, you can see they're changing. Next iteration, you can see all are now here. In the next iteration, you can see they're coming closer like. So likely you can find out the maxima or minima of this particular function. Clear? So this is the optimization by PSO, particle swarm optimization algorithm. Here, this is the accurate function. Now, the point is, already I have mentioned, the movement of the particle is dependent on the parameter. So now every evolutionary algorithm, every swarm intelligence algorithm, because as you are searching in the search space and it is a random search, so every search algorithm is based on two important performance that is known as exploration and exploitation. Exploration, how quickly you will explore the search space. So this is a global search. Exploitation is the find search, is the local search. Clear? So every evolutionary or PSO algorithm, you have to be a balance between global search and local search. Like if you have tuned your radio, you know, in the radio tuning, you have a coarse adjustment, you have a very fine adjustment. So if you do the coarse adjustment, then the red bar will move very fast. So once you are coming closer to the particular station you want to listen, then you do the finer adjustment. This is just like your tuning. So that's why in the exploration, I want to explore very quickly the search space at the initial period. So while the search starts, at the very beginning of the search, you must have a better exploration capability, that is better global search capability of the algorithm. But as the iteration comes closer to the predefined iteration, like I have told k equal to 1 to 8, or your number of iteration 1 to 1000, if you are coming closer to the predefined point, at that time what you want a local search there. That's why that is known as exploitation. So to control this exploration and exploitation, we want this omega value. Now you see, if your omega is very, very large, greater than 1, then your velocity will increase over time. Once the velocity, because it is omega VIK in dimension D. So this omega you are using with the velocity of the particle I in dimension D at kth iteration multiplied a inertia constant omega. So if we take omega greater than or equal to 1, then the swarm may diverge. So the omega value is generally taken between 0 to 1. So the particle will deaccelerate. Okay, and the convergence is also dependent on the value of C1, C2 or phi1, phi2. So that's why a large value of omega, when you need a large value of omega, when you starting search, you want to move with a greater acceleration. I want to travel from point A to B. Initially the road is free, so I can travel at 100 km/h. But when I'm closing to my solution, I can't travel, so I may cross it. So that's why you have to put a deacceleration in that omega. So at the initial period, omega must be large. At the final, as you come closer to the solution, search space, okay, the number of iteration in the search space, your omega should decrease. So large omega, better exploration capability, okay, global search. Small omega, better capability of the local search, that is exploitation. So that's why you have to make, instead the first paper of the PSO, omega was constant, 0.9. But gradual subsequent papers, it will change omega so that you can control the exploration and exploitation as the search progresses. So the very simple thing is, what you can do, you can change omega with the iteration. So now I can do, this is suppose iteration number, and this is your omega. So I can start at iteration number 1, omega equal to omega max. As the iteration decreases, the omega will be omega mean. So with the increase in the iteration number, as the search progresses, omega decreases from omega maximum 0.9 to omega minimum 0.3 or 0.4. So that is the another algorithm where they call the control, the better exploration and exploitation capability to the algorithm rather than giving a constant value of omega in every iteration. Clear? So that's why the classical particle swarm optimization is omega this. The particle swarm optimization with time varying inertia weight. So you can see the inertia weight omega is varied with a time varying C. The C is known as constriction factor. This is given by Maurice Clark. There is a paper by Maurice Clark, you can see. Okay, another way of omega you can see, omega is omega max minus omega mean into k max minus k by k max plus omega mean. So there are the different way how you can change this omega value and C1, C2 value. Okay, initial paper C1 and C2 is given as 2.1, 2.2, 2.1. So ultimately phi1 plus phi2 is 4.2 because C1 rand 1, the random number maximum value is 1. C1 is 2.1. So maximum value of phi1 is 2.1 and the maximum value of phi2 is 2.1, which is assumed in the initial paper. Okay, 1995. So this is a constriction factor PSO, which is proposed by Maurice Clark. So what they do, I have the same term VIK plus phi1 P best minus SIK plus phi2 G best minus SIK. The whole term is multiplied by a constriction factor X, where X equal to 2 by 2 minus phi square root of phi square minus 4 phi. What is this phi? This is phi1 plus phi2. So if you are taking phi less than 4, I have already told you 2.1, 2.1, phi1, phi2. If phi is less than 4, there is a slow convergence. Phi is greater than 4 is a faster convergence. Anybody interested in detail about this particular paper? This paper is by Maurice Clark. You can look into the paper by Maurice Clark and you can see how this constriction factor also. So this they call it constriction factor PSO. So three things very important which I have already told to you. I can control the omega, so I can control my exploration and exploitation capability. I can change phi1 and phi2 or C1 my C2. C1 is a factor which is responsible for comparison of P best minus SIK, that is my self-cognition capability. C2 is a factor which is giving to my social interaction capability. Okay, so C2 is compared with G best. So now omega, I have already told you, this omega max into omega max minus omega mean into iteration by maximum iteration. So for example, you are starting the iteration. So what will happen? Omega max is 0.9 minus omega max minus omega mean. That means 0.9 minus 0.3. Okay, multiplied by iteration is the first divided by total iteration by 1000. So you can see at the initial period, this is very low. So omega equal to omega max. As the iteration increases, when this iteration becomes 1000, this becomes 1. So this is 0.9 minus 0.9 plus 0.3. So ultimately, the omega is decreasing from 0.9 to 0.3 and iteration is increasing from 1 to 1000. So this is the very simple algorithm where omega changes as the iteration progresses. But is it the end of the solution? So some people, what they do, instead of fundamental principle is omega should decrease as the search progresses. But how it will decrease, it depends on you. How you make it, I don't know. So some people, what they do, they change it, keep the omega value constant for certain iteration, then you drop it, then you increase it for certain iteration, then you drop it, then you do like this, then you drop it, then you do like this, go like this, go like this. So they call it a staircase PSO. So this is same, but omega remains constant for certain number of iterations. For 100 iteration, it is 0.9. For another 100 iteration, it is 0.8. For next 100 iteration, it is 0.7. So you go, you call it a staircase PSO. I don't know how you are reaching from maximum to minimum. So some people, what they do, they just modulated with a sine wave. So they call it sine modulated PSO. Ultimately, this is the principle. Or somebody may modulate it with a wavelet, they call it a wavelet modulated PSO. Or what somebody does, they create a band, okay, between these two, and they generate a random chaotic number between these two bands. So they call it a chaotic PSO. So that means, see, the fundamental understanding is you are changing omega within a range and the range is fixed. So how you are changing it, ultimately from a high value to a low value, it depends on you and you will get the solution like that. So this is one idea how we can change this value of omega as the time progresses. Okay, so this is a comment on the inertia factor. A large inertia, better global search ability. Small inertia, a small omega, better local search ability. Okay, so by linearly decreasing, we have seen the inertia weight from a relatively large value to a very small value. So the course of the PSO, it run a better performance. Okay, as compared to the fixed inertia weight, because that is the logic here. You have embedded both global search and local search ability in your algorithm. Okay, within this particular algorithm. So this is very, very interesting phenomena in the PSO, and you can find a lot of paper which are dependent on this particular algorithm. Okay, so coming to the next, the flow chart. This is the flow chart of the PSO. It is very simple. You start, you initialize the particle. For each particle, you find out the position. You are given a velocity. I'm not going to repeat all these things. Already we have this. So these are the variant of PSO. There is a discrete PSO. It can handle the discrete binary variable. There are MINLP PSO. It can handle both discrete binary and continuous variable, because some variables are discrete, some variables are continuous, because it depends on the problem. A hybrid PSO, it utilizes the basic mechanism of PSO and the natural selection mechanism, which is by evolutionary algorithm or GA. You want to preserve the best particle, so you can hybridize PSO with some other algorithm. So there are enough algorithm you can find about the PSO. Now, I'll take a break after 5 minutes, but we have already seen how to change omega to get a new variant of the PSO. Now, the two other factors which govern also the dynamics of the particle in the subspace is C1 and C2. So what will happen if C1 and C2 both are 0? So if C1 and C2 are both are 0, you are only moving by your own inertia. You change it and go. Okay. But if you are making C1 0 greater than 0, but C2 0, you have a omega, but you don't have C2. That is only cognition model. You don't have C1, you have C2, that is social model. You have both C1, C2 greater than 0, then the particles are attracted towards your own performance and the best performance. That is Y and Y cap. Y cap is the tuple. If C2 is greater than C1, that means you are reliable on more global, on the social interaction in term rather than on the self. So that is more beneficial for unimodal problem. But if C1 is less than C2, okay, this is more beneficial for multimodal problem. So there are some criteria for the selection of C1 and C2, but the main, how can you make C1 and C2 adaptive? Like I have made, W is adaptive. The W is changing with respect to time. The W is changing as the search progresses. So how I can make this change in C1 and C2 as the search progresses? So maybe we can meet just after 5 to 7 minutes. Will it be fine? Hello.
Yes, sir.
Can we have a break for 5 minutes? Then we can start.
Yes, sir. Sure, sir.
Yes, sir.
Okay.
We will resume after 10 minutes break. I request everyone to be back after 10 minutes. Thank you, sir.
Okay. Okay.
Now I request Professor B.K. Panigrahi sir to resume on the session of swarm intelligence.
Now I am audible.
Yes, sir, you are audible now, sir.
So now coming to the change in C1 and C2. So now you see, there is a paper which is published in 2004 by A. Ratnavira, Salman K. Halgamuge, and H.C. Watson. So they call it self-organizing hierarchical particle swarm optimization with time-varying acceleration coefficient. So what they do, they change C1 and C2 with time or with iteration. So how they change it? T is the present iteration. Okay. And as the iteration progresses, so they decrease C1 from 2.5 to 2. So if I am plotting it, the C1 is decreased from 2.5 to 2. And C2 is increased 0.5 say 0.5 to, sorry, 2.5 to 0.5. And this one is increased from 0.5 to 2.5. So this is the value of C2 which increases and C1 which decreases. Can you do it reverse? In mathematics, you can just change in place of C1, you write C2, in place of C2, you write C1. But please try to understand, when I'm designing an evolutionary algorithm, so that's why all these algorithms are known as bio-inspired computing. They're inspired or they mimic the behavior of certain biology. So how they move. So now here it mimics the psychology. What will happen? Now there is a group of students. They are studying. They start from class 1. So if they start from class 1 at the starting of the iteration, I can't force them to compete with the topper. मैं हर टाइम उसको डंडा देके बोलूंगा कि नहीं टपर के साथ compete करो. So that let them explore their search space on their own at the initial period. As the search progresses, then put more thrust on the social interaction. So that is the main idea. The C1, which is the cognitive learning, which is the self-learning, at the initial, this is high. The social learning is low. As the time progresses, as the iteration progresses, the social learning increases and the self-learning decreases. So this is the main idea of this particular one. So either you can linearly decrease, linearly increase, or again, as already I have told you, you can do it by staircase type or something like that. Okay. So similarly, there are different methods on this. There is another beautiful paper also. They call it adaptive particle swarm optimization, self-coordinating mechanism with updating information. Same thing they do. That C2 equal to C2 plus A star B minus C2. That means the present value of C2, they only change C2. Okay, that will be and a factor. Now, what is this factor? You can see B is a statistical variable and A represents the influence about the previous social parameter. So how is the previous parameter and how is the suppose you are looking the previous parameter doesn't yield a good result, so you decrease. So it is continuously increasing or decreasing. But this paper I like very well. That is known as emotional particle swarm optimization. So you look into the emotion of the particle. How will you evaluate the emotion of the particle? How can I evaluate the emotion of a student after securing the mark in the class? So definitely, if the total mark is high at the end of the exam, that is at the end of the iteration, k equal to 1, k equal to 2, k equal to 3, all 20 particles are evaluated. One is the global best. So I can tell the global best is very happy. The worst is unhappy. So I will divide those particles into two groups. One group are sad, the another group is happy or joyful. So there are two sets. One set is a sad set, another set is joyful. So let me explain you. Suppose after the iteration k, you are finding the best particle is evaluated 500. The worst particle is evaluated 1000. Why I am telling this is the best? If it is a minimization problem. If it is a maximization problem, I can tell this is best, this is worst. So anyway, you know which is the best particle, which is the worst particle. So for minimization, this particle is the happiest, this particle is sad. So I can find out the mid 750. So any particle evaluating less than 750 is happy for the minimization problem. Any particle evaluating more than 750 is sad because the problem is a minimization. So at 750, I am making a boundary. It may change in the next iteration. So it may happen that in the next iteration, it comes 400 to 800. So my boundary now becomes 600. So this boundary changes at each iteration, but I'm dividing the whole particle into two groups. One group is happy or joyful, the other group is sad. So what I'll do, those particles who are sad, now you see the previous algorithm, irrespective of the particle, whether they are happy or sad, if the iteration is starting, I am giving everyone high C1, low C2. But here, why should I give high C1 and low C2? The particle is happy, it is performing better, even if in the class 1, even in the iteration number 1. So for that, I may make C2 is a bit more. So for those who are happy, for them, C2 is more and C1 is less. For the particle which are sad, for them, C2 is less and C1 is more. So this way, instead of a uniform value of C1 and C2, either C1 is low, C2 is high, or C2 is high, C1 is low, irrespective of the particle position, irrespective of the particle evaluation. Okay, so I'm making the particle into two sets. So here, those who are working in the fuzzy, so what will happen? Now I'm telling, let us 750. Suppose some particle is evaluating 749 and another particle is evaluating 751. But unfortunately, what I'm doing, if I'm making a crisp set, that is anybody evaluating less than 750 is happy, anybody evaluating more than 750 is sad. So I'm telling 751 is sad and 749 is happy. No, 751 is neither happy nor sad, 50-50. So its belongingness to both the set is almost 50-50. And 749, the belongingness to both the set is almost 50-50. So that's why I can tell, okay, if any particle is evaluating 400, it may be 90% happy, 10% sad. Any particle is evaluating 900, is 90% sad and maybe 10% happy in comparison to 1000. Because in 1000, the belongingness to sad state is 100%, happy 0. 500, happy 100. So you make a membership function. So this is, you can call the fuzzy PSO. So these are the various idea you will get by reading different papers, or you can incorporate your own idea how to modify all those algorithms. So that is the main idea of this algorithm, and to change the value of C1 and C2, to change the omega. So that's why this thing. Now there is another variant of PSO which is known as anti-predatory PSO. So what exactly we are doing in the PSO? The PSO, the particle learns from its own performance. The particle learns looking into the topper. But similarly, the particle also learns looking into its worst experience. If I have any worst experience, even if I have failed in a subject in second semester because I was reading that paper only once in a week, so I don't want to repeat that. So I can give here another dimension to the search in anti-predatory PSO. Anti-predatory PSO, the basic idea is, if the prey has fallen into the trap of the predator at some, I want to avoid that. So that's why the cognitive behavior, the self-learning behavior is divided into good experience and bad experience. If I have the best experience, that is P best. I may have a worst experience, that is P worst. So I want to go towards P best and I want to avoid the P worst. So P worst is given with a negative coefficient. So that is another dimension. You have C1 rand P best minus SIK, then C2 rand 2 G best. You can give C3 with a negative dimension, that is your worst minus present. You don't want to go there. I am here, I don't want to go there. Okay, so that's why this is known as the anti-predatory PSO. Similarly, the social behavior is also split into global good experience and global bad experience. You may follow a leader at some some iteration, a particular topper you have followed him, but you ultimately your performance was dropped down. So don't do that. So that's why the cognitive experience, that is C1, is divided C1 bad, C1 good. The social interaction C2 is also divided C2 good and C2 bad. So this is known as anti-predatory PSO. Clear? Then there are some neighborhood topology of the PSO, how the points are distributed in the search space. So that's why there are different neighborhood topology. I'm not going into that, how this neighborhood topology is there, but you can see a lot of literature are there in different type of the PSO. But if you have understood the basic philosophy, how the particles move, and a bit of the philosophy of the psychology, how we can control the movement, and a control theory, how can you control the movement of the particle in the search space, then definitely you can build up some new algorithm in that. So you can see the side particles are central by Maurice Clark. So M. Clark and J. Kennedy. The particle swarm explosion, stability, and convergence in multi-dimensional complex space. So this is a very good paper where you can get a lot of idea about the control strategy and control theory. Okay. Now, if we'll compare this with other algorithm, I know many of you know the genetic algorithm, where you know our evolutionary programming or evolutionary strategy, there is a method of selection, the best you want to select. But in PSO, there is no question of selection. And in genetic algorithm, the parent dies and a new offspring comes. But here, every particle is just changing its position, no question of die. Okay. And PSO is the only algorithm where you don't have to implement the survival of the fittest, like in genetic algorithm. There is no crossover in the PSO. But the most important thing already mentioned, you can have the movement of the particle in the search space, and you can keep a balance between the global search and local search ability by adjusting the inertia factor. So that is one of the advantage of the PSO in evolutionary in swarm intelligence algorithm. Similarly, you have other algorithms. So these are some multimodal function, because any algorithm you develop, you have to test it on the multimodal function. So I'm not going into all this detail of the function. You can get it in any of the websites. There is another algorithm based on the same principle by perhaps UEC, who is one of the author in the paper Everhart and C. That is pigeon inspired optimization. So it's the same thing. What is the pigeon? Because you know that pigeon is one of the bird which is having a homing behavior. And you know that during this World War and Second World War, First World War, Second World War, they are especially contributed to Australia, French, German, American, and UK forces. Okay. So it has the homing ability, and they move as per the sun and earth's magnetic field. And every pigeon is having a landmark, because they understand this landmark. They have to move according to that. Okay. So at the start of the journey, they rely more on the magnetic field of the map or magnetic field of the route. In the middle or end, they switch to the landmark. Some landmark comes, then they switch into that. So it is basically the navigation of the pigeon in the search space is governed by two things. Like already I have mentioned in the PSO. The same thing in TLBO algorithm, teaching learning based algorithm. Okay, in TLBO, the teaching learning based algorithm, there is a teacher and there is a learner. The teacher is nothing but the global west. The learner, so teacher changes in every class. Who is the global west? He will be teacher. So basically all the algorithm, the philosophy is same. But how you will change it, that depends on what is the new terminology you will give it to govern, looking into certain aspects, like how the pigeons move, how the bat algorithm, how the bats move, because you know that they throw out some frequency and there is a reflection, then according to that frequency they move. How the ant move. Once the ant will move, they will deposit some pheromone. So the more will be the pheromone concentration, more ant has moved in that way. So you follow that path, because that is the best path. So my point is, all these algorithms are dependent on certain mathematical principle, as well as that those mathematics you derive from the main biological principle. So that's why this is a pigeon based algorithm. So you can see in the pigeon based algorithm almost the same thing if you look into the equation. For pigeon I, okay, our I is the pigeon. Whether it is a pigeon or a particle, I don't bother. It has a position xi and it has a velocity vi. So this position and velocity of the particle, you have to update. So how this VIK plus 1? So VIK plus 1 is VIK, or VIT is VIT minus 1, the previous velocity, with a factor e to the power minus RT. So if you look into e to the power minus RT, this is a decreasing. Like your omega is a decreasing. So omega decreasing linearly, e to the power minus RT is decreasing exponentially. So please try to understand. That's why don't think that this is the some new algorithm or something new, but how you are giving a twist to your algorithm. Okay. So what I do to omega is linearly decreasing. Now e to the power minus RT, if r equal to 0, it is 1. Now it decreases to value 0. Okay. But how it will decrease? The more sharp, e to the power minus 100t will decrease sharply. But e to the power minus 2t, it will decrease like this. So this decrement from one value to the other value, or omega, this is indirectly omega in PSO. So don't be confused. Almost this is same. It is VIT minus 1 e to the power minus RT. I hope you understand. Okay. If it is a linear, so this will be linear decrement omega, but here it is exponential decrement, and this exponential decrement you can control whether the decrement is slow, that is r is low value, or the decrement is fast, r is very high value. And finally, this is nothing. Xg is the global best, xit minus 1 my present, so you don't have any comparison with your own local. Forget about that. So this is only, you can tell this is the social interaction based PSO. Okay. So this is a pigeon based algorithm. Now next xit is xit minus 1 minus in plus VIT. So I hope if you understand PSO, you can understand the pigeon algorithm. Only point here, there is no rand into x based minus xit minus 1. And instead of omega, VIT minus 1, it is e to the power minus RT. And this R is a map and compass factor. Rand is a random number and Xg is the current global base. So I hope you have understood this particular one. This is the global base, and these are all the pigeons in the search space. So they try, this is its original, this is its this one. So these two vectors, this is multiplied e to the power alpha t, then this distance is multiplied with a factor. So you will get a new vector like this. You will get a new vector like this. Okay. So likely you are getting all these new vectors. So this is map and compass operator. Similarly, this is the mathematical model. What they do for the landmark operator, the number of pigeons are halved after every iteration. Okay. So you divide it into two halves. So the pigeons are still far from the destination and are unfamiliar with the landmark. In that case, exit is the center of some pigeons at the teeth iteration. In the half, you take a center and suppose every pigeon to fly to that destination. So you can have an updation in PT, the total particle, you divide it into two, then you make a crossover xit minus xit equal to xit minus 1 plus rand xct. So xct is evaluated at the center. So this center, like you are dividing, half of the particle is divided as per that. So this is a landmark. You take a landmark, you take some particle in that, some pigeon in that, and find out and do the movement. Okay. So this is the basically the mathematical model of the PSO, of the pigeon optimization. Fine. So that's why this is the algorithm. I'm not going into the detail of the algorithm. I will provide you this. So till now we have discussed about the single objective optimization, where the objective is either to minimize or to maximize a function. And here I want to tell you one thing. One is the fitness function. Another is the function which is to be optimized. Okay, objective function. Objective function is to be minimized or maximized. But fitness function, you have to make the fitness. Now you see what is basically the fitness function and objective function. If I want to tell you, let us here I can tell. This is a blank page. So you want to optimize a function fx. So this is my objective function O. But what I'll do my fitness function, that will be fx plus some penalty p. This penalty is for the violation of the constraint. Because if there are certain constraints, so there are two types of optimization, either constraint or unconstrained. If it is an unconstrained optimization, the whole search space in the feasible region is the search space. But there may happen that I don't want a solution in this. So this is the infeasible region. This may be the another infeasible region. Even if I have a particle here and it evaluates the best among all the particles, but I cannot accept this solution. So if I cannot accept this solution, because although it is the global based, but it is violating some of the constraint and it is lying in the infeasible region. So what I will do, I have to give a penalty so that will be pushed from here to here rather than evaluating the global based, it will go towards the worst value. So remember, this is very, very important. So what I do, I have an objective function effects plus I am adding a penalty. So this choose of the penalty with some weightage omega is very important. You have to see what is your objective function range and what is your penalty range. Penalty such that it will predominantly overcome this objective function. For example, the objective range in terms of 1000 and the evaluation, this penalty violation in terms of 0.1, and you multiplied with a omega 1. So 1000 added with 1 into 0.1, 1000.1 doesn't carry any meaning. Still it remains the best. So that's why I have to give a penalty here. If it is 10 to the power 5 into 0.1, then becomes another 10 to the power 4 which is added instead of the global waste which is evaluating 1000. Now this will become 11,000 or something like that. So choosing of the penalty and choosing this penalty in which direction. If it is a maximization, now it is the best. What do you want to penalty? So you give a penalty in the opposite direction. So if it is evaluating 1000, but it is violating, I don't want a penalty to give it so that it will go 11,000. It becomes further better. So I will pull it downward. So 1000 may become 100. If it is a maximization problem, if it is a minimization problem, 1000 is minimum, but it is violating. I want to push it outside. So it goes to 11,000. Okay, no longer it remains. So please remember the choosing the value of omega and a proper direction, whether this is a positive sign or negative sign with the evaluation, it depends on whether you are doing a maximization or depend on a minimization. So this is a penalty factor based approach to handle the constraints in stochastic search algorithm, in PSO or GA or any algorithm to put it. But this is a single objective. I have only one objective. I want to minimize that objective or maximize that objective. But there may be some functions which is known as multi-objective optimization. There may be many objectives. For example, I want to minimize the cost of the product. If I want to minimize the cost of the product and simultaneously want to maximize the quality of the product. So if we look into objective 1 and objective 2, cost, you may not get a better quality. So if you want minimum cost, the quality will be down. If you want maximum cost, the quality will be high. So objective 1, minimization of the cost of the product, and objective 2, the maximization of the quality of the product. Although both objective I desire, but both objective move in opposite direction. So they are conflicting objectives. But if you look into objective 3, minimize the waste of raw material. Yeah, if I will minimize the waste of raw material, I will minimize the cost of the product. So 1 and 3 move in the same direction. Maximize the efficient use of man and machine. Again, it will minimize the. So you look into the objective. So when there are conflicting objectives, I call it a multi-objective optimization because there are two conflicting objectives. Some example, if there are any researcher who are attending this are from power system background, you may do economic emission dispatch. I want to minimize the cost of power production by n number of generators which are committed in a power system. And those generator power production cost is dependent on the quality of the coal you are burning. So if you are burning good quality coal, the cost will become higher, the emission becomes lower. Okay. But if you want to burn the low quality coal, the cost will be lower and emission will be higher. But what I want low cost, low emission. These are the two conflicting objectives. Similarly, I want to invest the money in the market. So when I want to invest the money in the market, what I want? Maximum return with low risk. It's impossible. If you will get maximum return, the risk involvement is high. If you are getting a minimum return, then the risk involvement is minimum. But as an investor, I want high return, low risk. No. The third problem, maybe many communication engineers, they do. You want to put the sensors. If you want to put the sensors, you want to put the sensor to have a better coverage. So if you want a better coverage, more sensor, more cost, okay, better coverage. But you want with minimum sensor, better coverage, I can't. So that's why these are some conflicting objectives. So when there are conflicting objectives, I have many objective, objective 1, objective 2 up to objective n, okay, subjected to some linear constraint and some non-linear constraint, and you want to minimize or maximize few of the objective. So how to do it? The simple way you can do, suppose there are two objective, objective 1 and objective 2. So you can give a weightage objective 1 omega 1, and objective 2 is given a weightage omega 2, which is 1 minus omega 1. So I can give now, for example, 0 weightage to objective 1 and 100% weightage to objective. So both the objective can be combined to a third object to make a single objective. So a multi-objective optimization can be converted to a single objective optimization by assigning a weight. So now please try. Your solution is dependent on what weight you are giving. Somebody may give no. I will give 10% weightage to this and 90%. 10% weightage to this and 90% weightage. So 0.1 and 0.9, you will get another set of solution. 0.2 and 0.8, you will give another set of solution. Likewise, you will get 1, 0. So 10 times you have to run this program to get a complete picture. And every time with a particular set of weightage, you will get a set of solution. So ultimately, you run the program, you convert the multi-objective to a single objective, assign the weightage, run the program multiple times, you will get a clear picture. And you can plot F1 and F2 in a two-dimensional plane, F1 and F2. But somebody tell, no, why I will go 10%, I will give 0, 100, then 1.1, instead of 0.1, 0.01, 0.99, 0.02, 0.98. So you have to run 100 times of this program. 100 times you run. Now, what is the guarantee? If you will run 100 times for any combination of the weight, you will get the feasible solution. You may not get. So that's why this is a very tedious task in converting the multi-objective optimization to a single objective optimization and choosing a particular weight. Another point is your F1, F2 dimension may be different. For example, I want to minimize the cost. So cost is either in rupees or in dollar or in euro, whatever. And the comfort. How can I measure the comfort? How can I measure the emission? Emission is the ton of carbon dioxide. So it has another unit. So I can't add 100 rupees with 1 ton of carbon dioxide equal to 101. I can. So I have to convert that 1 ton of carbon dioxide, how much rupee? So the conversion factor depend on whether you are developing country, developed country, I don't know. So that's why should I will bother. So I can't have two different objectives, having two different units, they multiply conversion factor. So the best solution is to have a multi-objective optimization is the Pareto dominant solution. So I'll discuss about here the single objective conversion. The result is dependent on weight. Some solution may not be reached. Multiple run is required to get the whole picture of the solution, and it is difficult to set the weight because the cost function may be at different scale. So that's why the solution is the Pareto based solution. So you convert your single objective to double objective. Okay, one objective is F1, another objective is F2. So what exactly you are doing? At every iteration, like in the previous, at iteration K, for each particle I, for a dimension D, you are updating, you are evaluating the function F, but you evaluate the function F1 and F2, both the function, and plot F1 versus F2. So if you plot F1 versus F2, you may get this. Let me tell you. Suppose at iteration number 1, you are getting, there are two particles. I'm only considering two particles. Iteration 1, two particles, one particle is at A, another particle is at B. So because for particle A, you have evaluated the value of F2, you have evaluated the value of F1. For particle B, you have evaluated F1 and F2. Now your function, you want to maximize A and B. So if you want to maximize both objective F1 and F2, both the function is to be maximized. F1 maximization, F2 maximization. So what I can see, if I compare these two solutions at a particular iteration, I can tell A is better than B with respect to objective 1, as well as A is better than B with respect to objective 2. So I can completely discard B. I don't need B because A is better than B with respect to all the objectives. So I can tell A completely dominates B. So this is the concept of dominance. A dominates B. Or you can tell B is dominated by A. Or you can tell A is better than B with all. But now let us, there are, in a particular iteration, there are three solutions, A, B, C, three particles. For each particle A, B, C, in single objective, you are evaluating F1 only. In double objective, you are evaluating F1 and F2. Now it map into F1, F2 plane. If I'll map it into F1, F2 plane, now you can see both are maximization. If simultaneously you want to maximize F1 and you want to maximize F2. So I can tell A is better with respect to B in objective 1 as well as objective B. So I can discard B with respect to A. Similarly, I can tell C is better than B with respect to objective 1 and objective 2. So I can discard B completely. But while comparing A and C, I can tell A is better than C with respect to objective 2 only. C is better than A with respect to objective 1 only. So I can't get a conclusion either A dominates C or C dominates A. No, but I can tell A dominates B, C dominates B, B can be out from this box. So there is a competition between A and C, both are non-dominated on each other. So this A and C are two non-dominated solutions. So what exactly you want to do, please try to understand. You have the iteration K. In that iteration, you have n number of particles, capital N number of particles. Every particle is have a dimension D. Once each particle is evaluated, they are evaluated with respect to all the function F1 and F2, support 2 by objective. Once they are evaluated, so all those 20 particles are compared with each other. So when they compare with each other, you may find some particles are completely dominated by the others. So you remove them. All these non-dominated particles you put in a basket. Those are the non-dominated solution. Then among those 20, you perform your updation of the particle. When you will go to K equal to 2, now again there are 20 particles. Out of the 20, the previous non-dominated 10 will be added up. So now you have a bag of 30. Among those 30, perform the non-dominated solution. You may get now 15 non-dominated. So you have 15 non-dominated transferred to the bag. Again, K equal to 3, you are generating another 20 new particles. In those 20 new particles, these old 15, which are already non-dominated, will be added. So the total strength will be 35, but you have to select again the set of non-dominated solution. So go on selecting this non-dominated solution in a packet, and ultimately you will get a Pareto front. So this finally the Pareto front set of solution. For example, the cost should be minimum, comfort should be better. It can't be. Okay, cost minimum, comfort minimum, cost maximum, comfort maximum. So you will get a set of solution. The user has a choice. Which solution I will choose? So if I have a good amount of money, I can go for this particular car where the cost is medium and comfort is medium. But if you have plenty of money with you, you may go for a car. Don't bother about the cost. Cost is high as well as the comfort is high. So what is the benefit of this algorithm? The benefit of this algorithm is instead of providing a single solution, you are providing a set of solution to the user. Depending on the user's requirement, depending on the user's choice, because all these solutions are non-dominated solutions, the user will choose a particular value of the solution. So that is the beauty of this multi-objective optimization. And how it is done, I have already told you that. The concept of the Pareto dominance. Okay. Now, this already we have done. So now, how will you get a good Pareto front? Now you can see, for example, here, you can get a Pareto front consists of this, or you can get a Pareto front consists of this, or you may get a Pareto front consists of this. You don't know. Or I may get a Pareto front consists of this. So there are 1, 2, 3, 4. But what is your algorithm results? So I can tell the Pareto front, which is here by the pink dots, is better Pareto. By this dot is not that much of better. So now, if your true Pareto is like this, the true solution is like this, you can tell almost you are reaching to the true Pareto. So this is known as the convergence of the algorithm. Whether all the Pareto front you are generating is converging towards the true Pareto. If you are getting a Pareto front like this particular one, okay, but your true Pareto front is this one, okay, this one, then I can tell the convergence is very, very poor. So there are two things. While generating the Pareto front by an algorithm, you see there is a multi-objective GA, which is known as NSGA, developed by Professor Kalyan Mahadev, non-dominated sorting genetic algorithm. Similarly, multi-objective PSO by Carlos A. Coelho. There are many algorithms, multi-objective bacteria foraging, multi-objective ant colony, multi-objective honeybee, whatever. But the concept is here, if you are getting a Pareto front of solution, and if you know the true Pareto, how closer your Pareto front generated by your algorithm to the true Pareto, that decides the convergence of the algorithm. Not only the convergence is important, I want also all the solution. For example, this is my true Pareto front. If I am getting some solutions here and some solutions here, then although the convergence is better, but the divergence is bad. Not all the particle is well diverged in this Pareto. Rather than if they would be like this, I can tell they are well diverged in the Pareto front. So the convergence and divergence are two important factors. Are the particles or is the Pareto front generated by your algorithm is converging towards the optimal Pareto? That creates the convergence. During that convergence, did all the solutions, all the member in the Pareto front are equidistant or they are well distributed in the Pareto front? That is known as the divergence. Okay, so these are the two important factors, two goals in the design of multi-objective evolutionary algorithm or multi-objective swarm intelligence based algorithm, to increase the diversity of the solution and to improve the convergence on the Pareto front. So that's why many strategy has been implemented, like Daiching and crowding and Pareto ranking and elitist strategy, so that they will move towards the global. Okay, so this is the multi-objective optimization problem. You can find out some issue in this, the fitness assignment, the density estimation and other things. So you can find NSGA, non-dominated sorting algorithm, developed by Srinivas and Dev in 1995. This is the pioneer work in this particular area. Then you can see Professor Kalyan Dev's website. Now he's not in Kanpur Genetic Algorithm Lab. You can see also the repository from Carlos A. Coelho, particularly evolutionary algorithm for solving multi-objective problems. Okay, so this is the idea of the multi-objective optimization problem. Now, some algorithm I can tell people are doing data mining, people are doing the many application of this. Now you see two things. I can tell to one important aspect. Let us here. I am designing a neural network. If I am designing a neural network, you are designing this neural network either for the prediction purpose or for the classification purpose. So here I want to give you one emphasis to all the researchers, because anybody working in PSO, GA, etc., they think that I need a mathematical function to be optimized, fx, not necessarily the optimization. For example, I have designed a classifier. So if I am designing a classifier, I am designing a neural network structure. What exactly I know in the neural network? If you look into the structure, you know the number of input and the number of output, but you don't know how many hidden layer will be there. You don't know how many neuron will be in the hidden layer. That means the structure of the neural network is purely dependent on your knowledge, how much hidden layer, whether you are taking single hidden layer, double hidden layer, or whether it is a swallow network or it is a dip network, having more number of hidden layer. But input output is fixed. So if input output is fixed, you can have a very complicated structure of the neural network like this, or you can have a simple structure like this. So if the structure is like this, then the complexity of the structure increases. If the structure complexity increases, it may give a very better nonlinear mapping between the input and output, and you may get a better solution, and your accuracy will be high and the error will be less. So high complexity, less error. High complexity, high accuracy. So if there are two objectives, one is the accuracy, another is the complexity. Complexity, or you can tell instead of complexity, the runtime of the algorithm. Because the more complex, the more processing will be there, the total algorithm runtime will be more. So you can have two objectives. One is the complexity, other is error. One is complexity, other is efficiency of the neural network, classification efficiency, training efficiency, testing efficiency, or you can give certain weightage to the training and testing. So remember here, when I'm giving a weightage to the training and testing, or when I'm making my testing accuracy, is the objective function. It is not explicitly defined by a mathematical function. So what I will do, I'll give, there are two subprograms. One subprogram is by neural network, where input and output is fixed. Okay. Number of pattern, 1000 is fixed. But what you are generating randomly, what you are searching for? You are searching for a structure. So suppose I am searching for a structure where the number of hidden layer is between 1, 2, 3. The number of neurons in each hidden layer is 10 to 20. So what I can do, I can generate a random number between 1 to 3, that is 2, generate a random number between 10 to 20, that is 15. So what I'll do, from my PSO, the particle 1 indicates 215. That data will be passed into the neural network. In the neural network, you know there is 2 input, 1 output, but now you are adding 2 hidden layers. Every hidden layer is having 15 number of neurons. The neural network structure is defined as per the particle 1. All the 1000 pattern will be trained and tested. You or out of 1700 is training, 300 is testing. With that particular structure, 2 input, 2 hidden layer, each hidden layer having 15 neurons, 1 output. The testing accuracy will be tested. Let the testing accuracy is 80%. So 80% is the objective function evaluation of particle 1. That means for 215, you are getting 0.8 as the objective function. So remember, again, I want to give emphasis. Many times the researchers get confused. Where is a mathematical function I want to optimize? Here it is not a mathematical function. You are passing the information from the PSO or GA or differential evolutionary algorithm, which is creating a structure of the neural network. Now you run the neural network program itself. It is an objective function. It evaluates the final accuracy passed on to the. Then you go to the particle 2. So particle 2, a random number between 1 to 3, let us 3, and a random number between 10 to 20, let it is 17. So there are 3 hidden layers and having 17 neurons. Let it evaluate. It gives you value 0.82. Now next 1, 10, it may give you 0.5. So likely there are 10 particles, and out of these 10 particles, you will give which is the P based, which is the G based. Now you go on. So that means here I want to give emphasis as a single objective. If you will make a multi-objective, okay. One objective is not the accuracy. With the accuracy, you find out the running time. So you will have a multi-objective optimization. So my point is, if it is a single objective optimization, you want to create an optimal structure of the neural network. You can do it by fixing the structure. If you want, no, I want an optimal structure, but I want the solution very quickly and with a reasonable time. So you may go for multi-objective optimization. So these are the some area where you have to focus your research and you carry out this research, this algorithm. Okay, coming to the next. Similarly, you might have done something on the decision tree, something on random forest. So you see, the simpler the structure of the tree, the more will be the error, the less will be the accuracy. The more will be the complicated structure of the tree, you will get a better accuracy. So this is accuracy and complexity trade-off. Clear? So this is a 2 objective Pareto front, particularly for those who are doing economic emission dispatch. The emission is ton per hour or kilos per hour or whatever. The cost is $1 per hour or rupees per hour. I'm not going into the details. This is the 3 dimensional. You can have fuel cost, emission, SO and NO. Earlier the emission was NO, then SO, So you can have a single objective, 2 objective, 3 objective. Nowadays many people are working on the many objective optimization. You can see many papers by Hisao Ishiguchi, who has done a lot of work on the many objective optimization. Clear? So this is one of the application I've already told you, because I'm a power person. So if there are any people on the power, I can tell a lot of application on the economic load dispatch, either it is a static dispatch or dynamic dispatch. That means what exactly you are trying to do, you are minimizing the cost of power production of n number of generator. So you have to find out power generated by generator 1, PG1 to PGN, and the summation of PG1 to PGN is the total power demand. So PG1 plus PG2 up to PGN, the summation is P load, if you are neglecting the losses. If there are losses, then P load plus losses is equal to total power generation. Similarly, there is optimal power flow. That because you are not solving the power flow only, simultaneously you are looking into the other constraint, the voltage violation, the line flow constraint. So you can have an optimal power flow, OPA. Many people are doing the DER placement. You have a distribution system. You calculate the loss in the distribution system. You want to put some generator in those distribution system. The question is, because I have to frame the optimization, I have to frame the search algorithm. What is the search algorithm? I have a 33 bus distribution system. I have a 69 bus distribution system. I know the loads in the system. Now my question is, where should I put this generator? So when the question comes, where can I go traditional search method? I'll put in, suppose it is a 69 bus. I'll put in bus number 2, bus number 3, bus number 4, bus number 5. So I have to calculate it 68 times. Then again, what is the amount? Suppose the amount is 0.2 to 0.5. So 0.2 bus number 2, 0.3 bus number 2, 0.4 bus number 2. So many times you run the algorithm. So instead of a sequential search, I'll do a random search. So in the random search, what do you want to generate? You generate two things. One is the position. So if it is a 69 bus system, you know your bus number 1 is your substation. You don't have to put a digi there. Now bus 2, bus 3, bus 4, then similarly other buses. So you go on. So what I'll do, I'll generate a random number from 2 to 69. That is the number of buses. And I will generate a random number between 0.2 to 0.8. That is the capacity. So suppose my first is 33 and 0.5. So what I'll do, I'll put a generator at 33 and the magnitude of that particular distributor generator is 0.5. I'll solve the load flow. I'll calculate the loss. The loss is the objective function. The second, suppose the random number is 50, the amount is 0.6. So at 50 bus, put a generator of 0.6, calculate the losses. So ultimately, I have to find out the best position. So that is the DER placement. Wherever you are doing, either it is a DER placement or a sensor node placement for the better coverage or something, so you can tackle this problem. There is a relay coordination problem. I want to put some relay somewhere else and I want to have a better coordination. Similarly, the simple example is the PID controller tuning, because you have to find out the parameter of the controller for which the system performance is better. So there is a lot of application where you can apply this swarm intelligence based algorithm, electrical engineering, or even if electronics engineering, or even if your classification, forecasting, etc., etc., etc. So many more problems where, because you have to formulate that problem very easily. Okay, so now, for example, this is a simple concept of the classical control. So you have a plant, then you have a controller. So if this controller is a PID controller, you know that for this, suppose this P controller simply, if we will change this value of the P controller, only one parameter to be tuned, that is Kc. If Kc is less, Kc1, you are getting this. You increase Kc, you will get solution. So with different, you are getting different set of solutions. So in one case, the low value of Kc, you know there is a steady state error. You increase Kc, the steady state error is decreasing, but the overshoot and oscillation becomes increasing. So there are many things. There are many effects of the controller. P control as well as I control. Okay, if we will change the I value at Ti1, Ti2, the time constant, because it is Kp plus integration Ki dt. So that Ki again. So if we will undesirable effect of the integral control, it increase the settling time, it reduce the stability, then there is an integral wind up. So what people do, so I have to find out the optimal value of Kp and Ki. But what is my objective? What objective do you want to achieve? The objective is minimization of the error. The objective is minimization of the overshoot. It should not. So either the overshoot you can put as minimization, or you can make the overshoot as a constant. I don't want more than 20% overshoot. So it is single objective optimization. The objective is minimization of the error. Subjected to the constraint is the settling time is between 10 seconds to 20 seconds. Okay, the overshoot is between 0.2 to 0.3. So you have to find out the set of parameter Kc and Ti or Kp and Ki so that the error is minimized. But with the minimization of the error subjected to certain constraint, the system should settle between 10 seconds to 20 seconds. The system should not have a overshoot, or if it has a overshoot, the overshoot between 0.2 to 0.3. So any overshoot more than 0.3 is not acceptable, or the maximum overshoot you can tell. The maximum overshoot is 0.3, because if you are accepting 0.2, you can accept 0.1 also. Okay, so likely you can have certain parameter, the optimization problem. So that's why these are the criteria. These are criteria. You can have integral square error. Your error, then you can the integral, the square of the error and integral. This is IAC. You can take integral absolute error, the absolute value of the error from 0 to infinite. But generally 0 to infinite doesn't carry any meaning. It is the system time simulation 0 to t. You can have ITAC, integral time. So E square t, you multiply with t, or integral time AE, mod ET. So these are the different objective functions you can design for your problem when you are going to find out the optimal gain of the PI controller for a particular application. Application is yours. But objective, you have to decide what is the objective, what is the constraint, whether it is a single objective, whether it is a multiple objective, that you have to decide. Okay, so looking into that, and similarly, suppose somebody is working on the fuzzy controller. So in the fuzzy controller, how to fit the optimization? Because you know that the error and change in error are fuzzified. So when you are fuzzified, what you are telling, this error is small, this error is medium, then this error is large. So who told you the small is a trapezoidal, the large is a trapezoidal, and the medium is a triangular membership function? I can tell this, I will change. And this trapezoidal may have this to this. This triangular may be unsymmetrical. So you don't know what is the optimal size of the fuzzy membership function. So that's why anywhere you want, you are searching for a solution, you don't know what is the best combination, you can apply your algorithm, or you can apply your random search method to find out the best fuzzy sets for the fuzzy control. Okay, because you are making a fuzzy set of error, you are making a fuzzy set for the change in error. So what will be those fuzzy sets can be decided also by means of the evolutionary algorithm or swarm intelligence algorithm. So these are the performance index like ISC and these properties, ITSC, IAE, and ITA. So that's why these are depending upon these property, penalize large control error, settling time longer than ITSC, suitable for high damped system. So depending on the nature of the system, you can choose any one of the performance index for your controller performance. Okay. So now this parameter, instead of a sequential learning, instead of a sequence change, suppose I know the KC range is 1 to 10, TI range is 0 to TI 0 means it is a proportional only, or you can take TI is 0.1 to 0.5. So you will have a large number of value. So why not tune it by PSO or GA or something like that with an objective? Okay. So this is a very simple thing. Now, another integration here we have done. I'll take maximum another 5 to 10 minutes. Is a solar PV system, because you know that in a solar PV system, these are the PV core. This is the voltage, this is the power. For a particular solar irradiance, you will get this PV core. So you can see the maximum power extracted from the solar PV module, okay, is dependent on the insolation and the voltage rating and the power rating. So this is the PV. You can have a fuzzy controller for this PV. You can have a PI controller for this PV. So this you can have also a very simple thing by quarter band observe method, because you have an initial solution, you make a slight change in the solution, you can go and find. So this is a traditional search method by quarter band observe. But if this PV curve is not having a single maxima, it have a multiple maxima. When it will result a multiple maxima for partial shading condition. Now you see there is no shading in the module. All the some modules are connected in series. So if you connected in series, the voltage increases. If you connected in parallel, the current increases. So you are getting this particular pattern. Now some of the modules are shaded. The shading may be because of the cloud. The shading may be because of the dust particle accumulated here. So what will happen? You will get this type of curve. Now you can see out of this type of curve, there are some local maxima, there is some global maxima, but you want to operate here. And in this case, this is your global maxima, because more numbers are shaded. So this is a global, this is a local. So once this condition arises, I can have a quarter band observe algorithm, okay, because they may trap, because quarter band observe is a local search method. So I can apply my random search method here to generate looking into a particular pattern, looking into a particular shadow pattern. I can have the algorithm, and this algorithm will decide you what is the value of the duty cycle of the converter, so that the maximum power can be extracted. So these are the case of the partial shading: cloud, tree, tall building, snow, dust particle, whatever. So here I have given pattern 1, pattern 2, pattern 3, and all these patterns are based on different irradiance condition. Okay, this is one pattern because of different shadowing condition. Shadowing condition and this pattern are different. So it may happen that at one time the shadow changes. So this is a dynamical type of optimization. For a particular time, a particular structure of the shadowing, you may operate at these practical GMPP or global maxima, but the next 10 second or 20 second, the global maxima shifts, because what will happen? The shadowing pattern changes. Then another shadowing pattern changes. So don't assume that the shadowing pattern remains constant throughout the time, because it changes with time. So although you have a shadowing, as the shadowing scenario changes, your global optimization also changes. So this is a very challenging task to find out the global optima, the operation. So here the objective function is to extract the maximum power for what value of the duty cycle. So that duty cycle 0 to 1, it is only one variable problem. So single variable search, you can achieve it by means. So we have done some testing in the lab, and all these algorithms, different algorithms are implemented to find out the global maxima in this particular one. So I'm not going into the detail. If anybody are interested, you can contact. We have done it in software as hardware, and the faculty, the student, the PhD student which have done with me and Professor Bhim Singh is now a faculty in IIT Jodhpur. Okay, so these are the different patterns you can see from one point to the other point, how the global maxima is changing, and we are able to track it. Okay, so I'm not going into the detail of this, because my main idea is to tell you some of the algorithm which can be implemented for certain purposes, and you can find out the solution. So let me complete here, and these are the hardware, because if you want to do it, you have to show some hardware result. So these are the hardware and software result. I'm not going into the detail. So these are the algorithm which we have developed. Okay, so let us, I'll close here and open it for discussion. Yes. Yeah, any questions? You can.
I request the participants to kindly unmute themselves and clear your queries. If anyone else,
Or you can type it.
or you can drop your message in the chat box.
Yes. Please ask question or type it in chat. Yeah. See, I have tried to give the emphasis of this evolutionary algorithm, but I know you are researcher of different area, different domain. So whether you are doing a classification problem by the neural network, whether you are doing a fuzzy controller, whether you are doing anything, but you have to look into how the swarm intelligence based algorithm will be applied to a problem. So the formulation of the problem is yours. How effectively you are formulating. Okay, there is a question in mechanical engineering, any specific domain problem? Yes, mechanical design, you are designing. When you are designing a particular structure of the system, you want the stability. Even if in civil engineering, you have truss design. So there are many variables which are having the different aspect of the design. Even in vehicle dynamics, you are controlling the vehicle dynamics, because I am actually heading the Center for Automotive Research. Many students are working on the vehicle dynamics, when it will go. So how much oscillation will be there? So there are a lot of application in mechanical engineering domain. But as I have told you, you are expert in your domain. So you have to find out how to fit this optimization, how to fit this traditional search or global search ability into your problem. You can find it out. Yes. And you know that particularly for the mechanical, if somebody is doing the job subscheduling, if somebody is doing the cost minimization, many people are doing particularly the job subscheduling. You can find a lot of work in the job subscheduling. The cost will be minimum, the total manpower requirement will be minimum, and the product cost will be minimum. So you can do a lot. Which algorithm can use in economic load dispatch under availability based tariff? Yeah, any algorithm you can go, but please try to understand all these algorithms. There is a theorem which is known as no free lunch theorem. So you can tell which algorithm is better, which algorithm is bad. So what you can do, the performance of each algorithm, as I told you, is dependent on the tuning of the parameter of the algorithm. So if you are using a PSO, and if you are using the PSO and you have tuned those parameters omega, C1 and C2 effectively for your algorithm, and a particular value of omega phi1 and phi2 may be better for your algorithm, for your application, may not be better for somebody else. So that's why please give emphasis in tuning of the parameter of the algorithm, whether it is PSO, whether it is genetic algorithm, how to select the crossover operator, how to select the mutation operator. So all these factors plays a very important role. Feature selection, yeah. See, this is very important point. The feature selection, because once you are doing feature selection, you don't know. Like I have given you an example of the neural network where there are two input. Two input means you have pre-decided there are two features. So how do you know these two features are best? Whether two features are best or four features are best or 8 features are best, because output is one. That is classification accuracy. So feature extraction or the selection of the feature for a better classification is an optimization tool. But the point is, when you are selecting the feature, either you can select the feature sequentially or you can select the feature randomly. So better go for random selection of this feature. But remember, some features are redundant. You don't know it. For example, if I want to classify whether it is a cow or it is a goat, if I tell the number of leg as a feature, then it doesn't carry any meaning. So if I'm taking 4, so this 4 is for the feature, 4 leg is for cow and 4 feature for the dog. Similarly, if you take the height, you may get a some certain feature, but it may not, because sometimes you will go for a goat where the cow is a dwarf and the goat is a surl. So that's why please try to understand, while doing feature selection, you don't know which feature is the best feature. So selection of the best feature is also an optimization task. Okay. What is crossover in optimization algorithm? Okay, this is actually in genetic algorithm we use crossover. There are two parent chromosomes. For example, the chromosome 1 is having bit 1, bit 2, bit 3, bit 4. Chromosome 2 is having bit 1, bit 2, bit 3, bit 4. And after this, I will exchange it. So this one, this one, this one, this one will be one child. Okay, then this one, this one, this one, this one will be another child. That means you generate a new set of solution from the old set of solution. That is another crossover. Okay, this is only in genetic algorithm. You generate a new set of solution from an old set of solution. Okay, so that's why perhaps you got the idea what is the crossover in this algorithm. Feature selection of intrusion detection system. Yes, you can see some of our papers. We do intrusion detection in smart grid. You can. PSO is used in electronic circuit, particularly the power minimization. People are using, if you have a circuit and you want to minimize the total power consumption in the circuit, people have used also PSO. Please look into those papers, because already I gave emphasis on you. You are the best researcher in your area. You have to fit this algorithm into your area. So whether it is optimal, which case it is optimal, because I have given you one beautiful example. If I want to travel from A to B, what is my objective? Is my objective is the shortest distance or my objective is shortest time? So similarly, when you are designing the electronic circuit, what you are looking for? Are you looking for the minimum number of components, or you are looking for the components are fixed, but I want to minimize the total power consumption of the circuit so that the battery life can be enhanced? So look into your objective and go for the design. Okay. Whether you use PSO, whether you use ant colony, whether you use bacterial foraging, whether you use differential evolution, forget about that. Or teaching learning based algorithm. Algorithm you can use on your own. But problem is yours. You have to design the platform where you have to dance. Clear? So dancing is selecting certain components for my dancing. If I want to dance in the footpath, then I will get a less money. But if I will do the same thing in a very nice auditorium, I will get more money. So look into your problem. Please try to understand. Look into your problem, design your problem as an optimization, either a single objective or multi-objective. Decide whether you want constraints or those constraints will be another objective, like I have told you. Then decide your algorithm. And looking into the complexity of the problem, looking into the variable, because what happens? Sometimes if the objective are binary type of thing, your variables are binary. You want a solution either 0 or 1. So in that case, genetic algorithm ant colony is best. Or there are continuous variable, you can go PSO, D. There are certain methods where, like I told, MINLP, PSO. You can go, you have certain binary variable, you have certain continuous. Suppose your manpower. You can't take manpower as a continuous variable. I have to take the manpower either 5 or 6. I can't have a solution 5.6 manpower. Okay. So that's why please look into your variable, how your variables are there, whether all the variables are continuous variable, all the variables are discrete variable or mixed variable. Yeah. I don't know how much I can impart it on you, but I think I have given certain basic understanding of those algorithms. And I always treat you are the best. You are the global best at present because you understand your problem, and to find the solution, whatever little guidance I have given or whatever little discussion I have, I hope it has inspired to you to go for the bigger thing. Because I give credit to all of you. You are the best programmer. You know all the language, whether it is a MATLAB, whether it is a Python or whatever may be the language, you know it better. And yes, you can do it. Like in the PSO, yes, I can do it. I based on my self-cognition power as well as the social interaction power. So every research is also guided by, every researcher should be guided by, that is my personal philosophy, don't take it otherwise. The self-cognition, yes, I can do it. And the social interaction, I will interact with my peer, I will interact with the good researcher in that area. At least I will go or search for the good papers published in that area to enhance my knowledge so that you will reach your goal. So learning is the combination of the self-cognition and social interaction, ultimately to get good result, whether the good result in terms of the publication, good result in terms of guiding students, or good result in terms of writing your PhD thesis. Okay. Any other question you have, or we may complete?
So I think there are no more questions left.
Okay, thank you.
Thank you so much, sir. It was great to have been taught by such an awesome professor like you, sir. I would really like to thank Professor B.K. Panigrahi, sir, for imparting us the knowledge about swan intelligence. And also, I would like to thank our Honorable Professor Sunil Gupta, sir, Vice Chancellor, Professor Vinay Thapar, sir, Head of the Department, and Dr. Keti Chaturvedi, sir, Program Coordinator, for organizing such an instructive session. Let me conclude by saying that there's no one thing that defines AI. It's more like a tapestry of modern intelligent technologies knit together in a strategic function that can then uplift and create a knowledge base that is automated, where you can extrapolate findings from them. Thank you everyone for your patience listening. Appreciate your time and support. Thank you again. Thank you so much, sir.
Thank you. So I
Thank
may
you,
leave.
sir.
Thank you.
Thank you, sir.
Thanks, Chaturvedi sir, and everyone, all the organizer, I thanks, as well as who has introduced me to this August audience. Thank you all. Thank you. Bye.